Hello friends, dear learners and my dear student. First of all, I welcome you to the lecture on ultraviolet visible spectrophotometry. I am Dr. S.R. Labhade, working as Associate Professor in the Department of Chemistry. Student, in previous lecture we discussed the terminology related with electromagnetic radiation and terminology related with absorption spectrophotometry. In today's lecture we discuss the fundamental laws of photometry, that is Lambert's law and B.S. law. The fundamental laws of photometry. First law is a Lambert's law. It was presented in 750. This law gives the relationship between absorbance and the path length of the solution. Lambert's law that gives the relationship between the absorbance and path length of the solution, and second law is called as B.S. law. B.S. law in 1852, this law is given. This law gives the relationship between absorbance and the concentration of the solution. There are two important laws of photometry. First law is called as Lambert's law. This law gives the relationship between absorbance and path length of the absorbing medium. And second law is called as B.S. law. This law gives the relationship between absorbance and the concentration of the absorbing medium. Student, we discuss each law in detail. First of all, Lambert's law. Lambert's law, the statement of this law when a beam of monochromatic light is allowed to pass through the transparent medium, the rate of degrees in radiant power, with the thickness of medium is directly proportional to incident radiant power. Here in this case, according to Lambert's law, when a beam of monochromatic light is allowed to pass through a transparent medium, the rate of degrees in radiant power with the thickness of medium is directly proportional to the radiant power incident upon the sample. Therefore, here, according to this law, here the absorbing medium is considered as a layered absorbing medium. Let us subdivide the absorbing medium. In this case, suppose this is a absorbing medium up to this. Suppose a radiant power of 100 intensity is passed, and if each layer absorbs 50% of light, then here 50% would be absorbed by this layer, 50% would be given on next layer. Out of this 50, 25% is absorbed here, 25% is given next layer. Here 12.5 absorbed and 12.5 given. Here 6.25 absorbed, 0.125. That means here when we pass a light of intensity 100 through a 4 successive layers, the outcoming light will be have intensity or 3.125%. That means here radiant power absorbed by first layer and remaining will be transmitted to second layer. Depending upon the absorbance, radiant power is absorbed by the medium and remainder is transmitted. Therefore, here these 4 layers gives only this much light when 100% intensity light is passed through this solution. Therefore, here we can write this in this way. Each absorbing layer have identical thickness of, suppose this is a dB, that is a small layer of thickness dB, and each layer absorbs 50% of the incident radiation. Therefore, and 50% of it transmitted. Suppose for example, the first layer absorbs half of the incident radiation of the radiation incident upon it. Then second layer will absorb half of the radiation incident upon it, and the radiant power emerging from second layer will be 1/4 of the original power. Similarly, from third layer, it is 1/8 of the original power and so on. That means in this case, in Lambert's law, absorbing system is considered as a layer. Suppose for example this is a 4-layer absorbing system. In this case, if we irradiate this system with 100% intensity of light, and if each layer absorbs a 50% of incident light, then 50% will be transmitted through it. Suppose for example if first layer absorbs half of the radiant power, then second layer receives half of the radiant power as an incident radiation. Then second layer again absorbs 50% which is received from the first layer. In this way, the radiant power emerging from the second layer is 1/4 of the original radiant power falling on the solution or falling on the first layer. Similarly, the radiant power emerging from the third layer is equal to 1/10 of the original radiant power. In this way, here the radiant power is decreases in the solution. But here you will say that, or you will find that the transmittance of each medium is identical. That is, here radiant power is 50% absorbed, 50% transmitted. Therefore, for this first layer, T is equal to 50 divided by 100. For second layer, it is 25 divided by 25 divided by 50. For third layer, it is 12.5 divided by 25. For third layer, it is 6.25 divided by 12.5. That is equal to 0.5. That means transmittance of each layer is identical. Because here each solution absorbs equal amount of radiant power, therefore transmittance is identical. So in this case, the rate of decrease in radiant power with the thickness of medium, therefore the rate of decrease in radiant power with the thickness of medium is directly proportional to radiant power or incident radiant power. Therefore, here mathematically this statement may be written like this: minus dP by dB is directly proportional to P. Here dP by dB, that is rate of change in radiant power with the thickness, is directly proportional to incident radiant power. Here negative sign indicates that radiant power decreases with the thickness of the medium. Now here, in this case, if we consider a 10-layer system, suppose for example we have a homogeneous system of 10 layer, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like this. Here this is a 100% incident radiant power, 50%, 25, 12.5, 6.25, 3.125, then 1.56, then 0.78, then 0.39, then 0.19, then 0.98, and here emerging is 0.49. Therefore, here as the number of layer increases, the radiant power emerging from layer that get decreased. Here in this case, if we increase now in this case transmittance of each solution is, each layer is same as we calculate here. But here suppose if we linearly increase the path length, then what is the effect? Suppose for example this is the first layer, this is first layer. In this case 50% is transmitted. This is a second layer, this is a third layer, and this is a fourth layer. For this B is equal to 1, B is equal to 2, B is equal to 3, and here B is equal to 4. Therefore here in this case if 100% light intensity falls on first layer, 50% is transmitted and 50% is absorbed. Therefore, this figure is equal to transmitted and the absorbed light. Therefore, here it is 12.5% transmitted, here 1.56 transmitted, here we can write transmitted, that is 50, here transmitted is 12.5, here transmitted is 1.56, here transmitted is 0.098. That means here in this case first layer intensity is divided by 2, for second layer transmitted, that is 50 divided by 4, for third layer 12.5 divided by 8, and for fourth layer 1.56 divided by 16. That means here if B is increasing T, we have T is equal to, for first layer T is 50 divided by 100, for second layer T is equal to 12.5 divided by 50, for third layer 1.56 divided by 12.5, for fourth layer T is equal to 0.098 divided by 1.56. Therefore, T is equal to here, T is equal to 0.5, T is equal to 0.25, T is equal to 0.125, and T is equal to 0.0628. That means here this is a transmitter's value. Therefore, transmitters in the first layer having B is equal to 1 this much, when B is equal to 2 this much, when B is equal to 3 this much, when B is equal to 4 equal to this much. That means in this case, if we plot a graph of transmitters as a function of path length, increase in path length, then we have a curve like this. T is equal to, in this case, P upon P0 versus B, that is a path length. In this case, path length is linearly increasing. And therefore here, initially we have T is equal to 0.5, means it is a higher value that get decreases exponentially as path length decreases. In this fashion, we have a curve. This curve shows that exponential decrease in transmitters as path length increases. Therefore, here transmittance is not inversely proportional to path length, because it is exponential decrease in path length. decrease with path length. Therefore, transmitters is not inversely proportional to path length. Therefore, here this is the relationship we found with the transmitters and the path length. And mathematically, we can have this relationship and we can now obtain that in the equation, and that is we derive the Lambert's law. Therefore, here we find that transmittance of each layer is identical, but if we increase the path length linearly, then we observe the exponential decrease in transmittance. Student, now we derive the equation for Lambert's derivation of Lambert's law. According to Lambert's law, when a beam of monochromatic light is allowed to pass through the transparent medium, the rate of decreasing radiant power with the thickness of medium is directly proportional to incident radiant power. Therefore, mathematically, this law can be represented like this: minus dP by dV is directly proportional to P. That is rate of change in radiant power is directly proportional to incident radiant power. This is represented in this equation. In this case, dP is a small change in radiant power. dB is small thickness of absorbing species or a solution, and here negative sign indicates that radiant power decreases with path length, and we can derive this law for determination of absorbance of solution. Therefore, here on rearranging we have this minus dP by dV, minus dP by P is equal to K1 into dV. On rearranging, then we integrate this equation on integration with the proper limit. Here minus dP by P, P0 to P is equal to K1 into integration of dV, B is equal to 0 to B is equal to B. Then we have integration of this is minus ln P, here P0 to P equal to K1 into integration of dV is B from 0 to B. Therefore, here when we put this value into this equation, then we have here minus ln P upon P0 is equal to K1 into P. Therefore, here this equation, in order to eliminate negative sign, we can write ln P0 upon P is equal to K1 into P. Therefore, here multiplying with 2.303 to convert natural logarithm to log to the base 10, we have this equation K1 into P. Therefore, here log of P0 upon P is equal to K1 upon 2.303 into P. And here log of P0 upon P, we know that it is called as absorbance, is equal to K1 upon 2.303 into P. Therefore, A is directly proportional to B. This is the Lambert's law. Therefore, rate of change in radiant power with the thickness of medium, that shows the exponential decrease in transmitters with the path length, but here absorbance is directly proportional to path length. That student, this is about the Lambert's law and derivation of Lambert's law. In next lecture we discuss B.S. law. Thanks for joining with me. Wish you all the best. Keep learning. Happy learning.